So a reminder, 1 week from today, our first exam over Chapter 2. So you want to make sure you're getting your homework done and the quiz for Chapter 2. Are there any questions before we start today? If you want to email me instead of asking in front of class about specific homework questions, feel free to email me, and I'll discuss those problems as well. We left off in 2.5. With this last example, we were looking at the end behavior of e to the x. And so our two end behaviors there, as we approach infinity, the function approaches infinity. At negative infinity, the function approaches 0, which again is like the horizontal asymptote, not in a more traditional sense that we're used to seeing, but on the negative side of e to the x, it does approach 0. So, were there any questions on this example? Yeah.
So, I guess what I'm a little confused about is as something approaches 0, it never, like, or a horizontal asymptote or whatever, it never hits 0, so technically goes to infinity, right?
Yeah.
So why do sometimes you put 0 and sometimes you put infinity?
So the like when we're computing various limits, is that what you mean?
Right, yeah.
Yeah, so the limits, let me add a page here. The limits that come out of the form, when we evaluate a limit and we get like some fixed number over 0, what does that approach?
0.
Well, the numerator is fixed, the denominator is getting smaller and smaller, so what happens to that quotient?
Goes to infinity.
Yeah, it gets larger and larger. So this thing approaches infinity, but kind of interchanging the role of infinity and 0 here, if you've got a fixed number whose denominator approaches infinity, then the fraction gets smaller and smaller. And it doesn't matter if this is positive or negative, or the numerator n is positive or negative. 0 is 0. So, I mean, symbolically, it's just that we like interchange the place of these and we get the other.
Oh, okay.
So yeah, that's those two concepts you've got to know, because we have seen a lot of limits that ended up with, the numerator is fixed, the denominator is getting smaller and smaller, closer to 0. And where the numerator is fixed and the denominator is getting larger and larger. So we've seen those, and we will continue to see those whenever we look at limits. Is that helpful? Is that what you're asking about?
Yeah.
Okay, yeah. And in the sense of, x approaching infinity and y approaching 0, we never cross, well, sometimes you can cross a horizontal asymptote, but, we would expect for super large values that it's really, really close to 0. We're not saying that as the function approaches 0, the function, or as x approaches infinity rather, the function is equal to 0, right? We're just saying as x approaches infinity, the function approaches 0. Yeah, thank you. Any other questions? All right, so the last example in 2.5, what is the end behavior of the natural logarithm? And again, maybe you remember what the graph actually looks like. So this one's just slightly different because I think up to this point we haven't looked at end behavior on functions that have a restricted domain. So does anybody remember the domain for natural log?
Is it negative infinity to 0?
Not negative infinity to 0. It's the other one.
It's negative to infinity.
Yeah, 0 to infinity. So we do have to remember the domain of these functions, because computing an end behavior at infinity and at negative infinity on a function such as this doesn't make sense, because the function's not defined for negative numbers. So the end behavior really, in one direction, it's like the others. The limit as x approaches infinity, that's going to give us one end. But to determine the other end behavior, we would compute the limit as x approaches what? Zero, yeah, zero, but more technically speaking, I'm only allowed to approach zero from the right. So that's the other end behavior of this function. So just, keep that in mind. When you're thinking about end behavior, you're just thinking about on whatever function I'm dealing with, what's happening on the ends. And certain functions do have restricted domains. So as x approaches infinity, the natural log approaches what?
Is it infinity?
Infinity, yeah. It's not obvious at all that natural log approaches infinity when you look at a graph. So the problem with the logarithms is the logarithms, other than like a constant function that never grows, logarithms are some of the slowest growing functions that we have. So we're relatively close to the origin. We can definitely see that growth. But as we get further and further out, it starts to look like that logarithm actually flattens out. And that's just because its growth rate is so slow. So even for an x value of 2,000, the log of that's not even 10 yet. Or what is that, 20,000, my bad. So for 20,000, the output is still 10. So, for these extremely large outputs, the logarithms have very small inputs, or outputs rather. I said that the other way around. So what is that? 320,000, the log is not even at 13. So, again, don't be fooled by the graph. This function does actually continue on to reach a y value of infinity, so to speak. But we might not guess that from the graph. I mean, I know perhaps when we drew the graph in a prior course, we would say here's this point at 1, 0, and the logarithm just does this. So we kind of over-exaggerated the fact that it kept growing. The other way to know that for sure is to relate it back to its inverse function. So what if the function f is the natural log of x, what is the inverse of that? What undoes a natural log? If you've got a natural log in an equation and you want to get rid of it, what do?
E.
Yeah, you involve e. So if e to the x is the inverse of the natural log. And then if you can remember, when we talk about inverses, we say that the domain of the inverse function is the same thing as the range of the function. And the range of the inverse is the same thing as the domain of the function. So that's also another way to think about, does the logarithm actually grow to infinity? Well, we have to look at the range of the inverse function, and the range of the inverse function does go off to infinity, therefore the domain of the logarithm goes off to infinity, and the y values do as well. So here's approaching infinity, and the y value is also approaching infinity. So that's on one end of the logarithm. The other end, we've got to compute the limit as x approaches 0 from the right. Again, based off of the domain. So the limit as x approaches 0 from the right on the logarithm gives us what? Natural log, rather.
Negative infinity?
Negative infinity, right? Which means now as x gets closer and closer to 0 from the right, the function values approach the negative infinity. There's a vertical asymptote on the logarithm graph at x equals to 0. Okay, so those are helpful if you see limits where it says, for instance, evaluate the limit as x approaches 0 from the right on, let's say, x minus 1 over the natural log of x. So we know that our denominator, ln x, as x approaches 0 from the right, approaches negative infinity, and the numerator is approaching -1. So we've got a fixed numerator, denominator that's getting larger and larger and larger. What happens to the quotient? Yeah, it gets smaller and smaller and smaller. So, if you're still kind of confused on some of the limit stuff, when we write equals to with a limit in the context, think about it as another way of saying approaches instead of actually, like an equal sign we usually read is 0. In the context of a limit, it says that this function approaches -1 over negative infinity, that approaches 0. So the equal sign might be misleading, I don't know.
You can put like an arrow on the end of the equal sign.
Yeah, we put an arrow. Somehow this is just traditional to write equals to. Yeah.
So when we look at that function, for instance, if we're looking at, for instance, at the end behavior, x goes to infinity, since the numerator and denominator both go towards infinities, but we don't know if they're like at the same rate, how would we determine what the end behavior of that would be?
Okay, so that's a really good question. So did everybody hear the question or understand the question? Let me reformulate. I think is what you're asking. What if I had the limit as x approaches infinity? So I'm computing the end behavior on some function. Let's say it's f of x over g of x. And I determined that the numerator is approaching infinity and the denominator is approaching infinity. Is that what you're asking about?
Yeah.
So what would that mean for us?
Would be 1.
So that's a good guess. It's a misconception though, because remember infinity is saying as x goes to infinity, the function on top is growing arbitrarily large and the function on the bottom is growing arbitrarily large. If in fact they are growing at the exact same rate, we can say that it's always 1. But one of these functions could very well grow a lot faster than the other. The good news is we don't see this until 4.7.
Okay.
So this is like way on down in the semester. These types of things can have any value. A lot of times, in every instance, we do have a means to compute those types of limits, and we do see that they become a specific value. But if we just look at it in the sense of infinity over infinity, that can have any value. It really depends on the function up top and on bottom. We call these things just, looking ahead, they're called indeterminate forms. Indeterminate forms. I believe it's 4.7. So we do actually cover those. So it's the same thing for, and here we mean either positive or negative infinity on top and bottom. Or it could be 0 over 0. 0 over 0 in the sense of the numerator approaching 0 and denominator approaching 0 is also an indeterminate form. It could have any value. It's up to us to determine what is its value. But unfortunately, we don't look at growth rates in this class anymore. Growth rates are super, super helpful to determine these types of limits too. But that's not something we actually look at anymore. We do talk about these limits, however. Yeah, good question. Any other questions? All right, we'll conclude 2.5 then, if there aren't any more questions on that section. So 2.6, we're talking about the notion of continuity. You have seen an informal definition of continuity before. So our informal definition, maybe in algebra class, was a function's continuous if I can draw the function without ever having to pick up my pencil. That's how we define continuity. So example, the function on the right, this is a continuous function. The function, sorry, on the left, the function on the right is not continuous or discontinuous. And in most instances prior to this course, that was a very adequate definition, because we look at both of those functions and we can clearly determine which one's continuous and which one's not continuous. However, it's not sufficient to cover every single kind of function. For instance, this h of x function that's given here. What if we wanted to know, is this function continuous at 0? Do we have to pick up our pencil to draw the other squiggles on the right side, or can we just go straight through to 0? If we looked at the function's definition, there might be varying opinions. Well, the function is defined at 0 on the bottom piece, but it's not defined at 0 on the top piece. I know I can't take the sign of 0, which is why the top piece isn't defined at 0. But that doesn't really help us determine, is there a hole at that point or that location? What's happening at the origin? So that's just a motivating example to show us that we need a better definition of continuity. This section is very technical in how it presents material to you. I'll write it down at some other point, but as we move forward, I want you to try to remember that when we're talking, when these problems are asking where is this function continuous, it is no different than asking what's the domain of this function. Okay, so you all have done this time and time again. We're just going to put a different label on it and look at it in a different context. So think about associating continuity with domain. There are some exceptions which we'll point out, but continuity and domain, pretty much the same thing. Okay, so we need a better definition. Here's our definition of continuity at a particular x value, or at a point. So a function is continuous at a, this is our x value, if the limit as x approaches a on the function is identical or equal to the function value at a. If f is not continuous at a, then a is a point of discontinuity. Okay. So really what that definition boils down to are three different things we have to ensure. We have to ensure that this f of a, the y value at that x location, is actually defined. Then we have to ensure that the limit as x approaches a is defined. But again, that's not enough to justify continuity, because then those two things, the limit and the function value, have to equal each other. So the continuity checklist is a breakdown of the definition in a working sense. So when we're asked to justify if something's continuous, we need to justify all three of these steps. And they're nested. If one fails, then the other fail. If one's true but two fails, then it still fails. If 1 is 2 and 2 is true, notice the statement in number 3, or item 3 in the checklist. Statement 3 is just asking, does 1 equal 2? So there's 1, and there's 2. In the sense of the numbers here, not 1 equals 2 is a mathematical statement. So you do want to be familiar with these. On the exam, if I ask about continuity, then I'll ask you to state which one of these conditions fails to justify places where a function is not continuous. But the continuity checklist is just a more detailed viewing of the definition. So with the definition of continuity in mind, we can turn back to the function h of x to determine if it is continuous at a point, x equals to 0, y equals to 0. So check if the function to determine if it is continuous. So when you see determine if something is continuous, start thinking about those 3 checklist items. I have to justify all 3. We're determining if this function is continuous at an x value of 0, so that 0 is now taking the place of a in the definition. So the first item on that checklist tells us, does f of a, or is f of a defined? In other words, in this function h, can we define f of 0? Sorry, that's very confusing because the function isn't f, it's h. Sorry about that. So is h of 0 defined? Yes, what is it? 0. H of 0 equals to 0. The second piece we have to use. So that's item number 1, f of a is defined. Item 2 says that the limit on that function also has to be defined. The limit as x approaches what? 0. That's the point in question. The location of x in question is 0. So we have to make sure that the limit as x approaches 0 is defined. So if x approaches 0, which piece do we use? The top or bottom? The top piece. Why is that?
It's not exactly 0.
Because it's not exactly 0, right? Remember, the limit doesn't care about that value. It cares about all values around it. So x is merely approaching 0. It's not equal to 0. We have to use the top piece. So we're still trying to answer the question, does that limit exist? If that limit doesn't exist, there's no way for 1 and 2 to equal, which means that the function would not be continuous. So here's a function, it's a trig function. We can't simplify it. What's our approach with stuff like that we've seen anyways? Yeah, we sandwich it or squeeze it in between 2 well-behaved functions. Oh, I'm running out of room. All right, we'll try to squeeze this in here. So we just have to remember the fact that the sign of something is always in between 1 and -1. And then to get our sign of 1 over x in our inequality to look like the function involved in the limit, all we need to do is multiply it by x. So if I multiply this middle piece by x, I have to multiply all pieces by x. So now I have that x sine 1 over x in between negative x and positive x. Does that help me with the limit as x goes to 0? So the limit as x goes to 0 on this function would be what? Yeah. If I look at the limit as x approaches 0 on all three of these functions, as x goes to 0, negative x goes to 0. This middle piece is the limit as x goes to 0. We don't know about that yet. And 1x approaches 0 as well. Therefore, our limit does equal 0. Let me write this here. The limit as x approaches a on whatever function we're talking about is defined. So that's item 2 from the checklist. And then item 3 is just asking, do those two things equal each other? Yeah, both of them are equal to 0. So the limit as x approaches 0 on h of x equals h evaluated at 0. So what's our conclusion?
It's continuous.
It is continuous. So that function h is continuous at the x value of 0, meaning we can, get those squiggle through the origin and not have to pick up our pen. Therefore, h of x is continuous at x equals to 0. See, it doesn't get any better as we get closer and closer. Is by itself, is the function x sine 1 over x, is this function that's graphed here defined at 0? No, how do we know?
0, or sine of 1 over 0 doesn't exist.
Right, because we can't compute the sine of 1 over 0. That value doesn't exist. So, and that's where that second piece comes in of the function h. The second piece says that I'm going to define the function at 0 when x is 0. In other words, that second piece comes in to where x sine 1 over x has a hole, and the second piece comes in and fills that in. So without the piecewise definition of that particular function, x sine 1 over x wouldn't be continuous at 0. Why wouldn't this? We said that the reason why it wouldn't be continuous by itself, x sine 1 over x, is because the fact that the function doesn't even exist at that value. So there's no way for the limit to exist and the other things to equal. Does that make sense? It's the reason why it's put together as a piecewise function. But if this is our function, x sine 1 over x, we would say it's not continuous at x equals to 0, and our justification is checklist item number 1. Or sorry, f of 0 is undefined. Does that make sense, Gil? The piecewise function that we worked with came in and said, well, this x sine 1 over x isn't defined at 0. Let me add another piece to it that makes it defined at 0. And then we can kind of check continuity that way. But as a standalone, it's not. Do you have any questions on that? All right, another example. We're going to use the figure to determine where the function is continuous, where the function is not continuous, rather. And it says use the checklist to justify your answers. Okay, so it doesn't matter the order. Just start listing the values where the function is not continuous and justifying why that's not the case, why that is the case. So what x value is the function not continuous? There's a bunch.
One.
Okay, x equals to 1. Why isn't the function continuous at x equals to 1?
F of 1 is undefined.
Right, the first item in the checklist. We can't define f of 1. Okay, what's another value of x? At x equal to 2. Okay, why is the function not continuous at x equal to 2?
Because the limit as x approaches 2 is not equal to f of 2.
Right. So the first item asks, does f of 2 exist? Yeah, f of 2 exists as that point up there. Does the limit as we approach 2 exist? What's the limit on that function as we approach 2? 1. So the limit exists. However, the limit 1 and the function value 3 aren't the same. So we're talking about number 3 here. F of 2 does not equal the limit as x approaches 2. Well, I guess that's F. So I know, hopefully, it's very easy to look at a graph and completely determine where it's not continuous. The problem with that now is we've got to actually state why it's not continuous in the sense of a limit or the checklist, rather. Okay, next x value.
3.
X value of 3. Why is that function not continuous at 3?
Same reason as number 2.
Okay. So is the function defined at 3?
Yeah.
Yeah, the function's defined at 3 at that point, but the limit as we approach 3 doesn't exist. Why doesn't the limit exist?
Because it's not two-sided.
Right, as we approach 3 from the left, we get 2. As we approach 3 from the right, the limit is 1. So the limit as x approaches 3 does not exist. And if we wanted to be more specific as to why that limit doesn't exist, we would just say that the limit from the left does not equal the limit from the right. Okay. Any other x values where the function's not continuous?
5.
At x equals 5. Again, I think we all clearly clearly see that. Why is it the case, though?
There's a vertical asymptote.
There's a vertical asymptote, and that's absolutely correct. But in the sense of the checklist, which item is not holding? Number one, if you've got a vertical asymptote, your function cannot be defined there. So please try to use these things. Like on the exam, don't say because there's a vertical asymptote. Don't say that. At x equals to 2, don't say that it's discontinuous because there's a hole. That doesn't make sense. I mean, there is a hole there, but what does it mean? Why do we have a hole there? So explain these things in one of 3 ways, not visually. Does that make sense?
Are we gonna be supplied the list, or is that something we just need to hold on to?
You have to remember it.
Okay.
Yeah. Unfortunately, there's not a lot of things we can provide on the exam, so most of these things you end up having to remember. The final exam, you can have a note card, but not on any other exam. Okay. We're not going to worry about this endpoint here. We haven't talked about continuity from one side or the other yet. So those are all the values at which that function is not continuous. Do you have any questions on that? My hope is that you can clearly see that, but it does take a little bit of finesse when we start using the continuity checklist. So start studying that. Okay, here's 2 examples. And we want to know, given the function f, is it continuous at a? So example 1, given 3x squared minus 2 over x minus 1, is that function continuous at an x value of 1? No, we can clearly see that. Again, a lot of these functions, continuity and the domain of the function are virtually one and the same kind of concept. So we clearly see that this function is not defined at 1. No. We don't care if it's an asymptote or a hole. Doesn't matter. The function's undefined there. There's no way it can be continuous there. Is function 2 continuous at x value of 3 and an x value of 4?
So if a graph has or if a function has multiple reasons why it's not continuous, do we have to list all the reasons or just one reason why it's not?
So there's always one reason why a function's not continuous. Even though we have 3 checklist items, let's go back to those. Even though we have 3 checklist items, they're built off of one another. So if one isn't true, then there's no way 2 can be true. So if 1 and 2 aren't true, if both of those happen to be not true, we stop at number 1 because the function's not defined. If both of 1 and 2 are true, but 1 and 2 aren't equal to each other, then we cite number 3 as the reason why it's not continuous. So yeah, when you're justifying if a function is continuous at a point, you're only going to use one of these to state why it's not continuous. You don't have to list the others because it's inferred. Yeah, good question, thank you.
So can't 2 be true if 1 isn't true?
2 can be true if 1 isn't true. So the function doesn't have to be defined somewhere. So if we did this, if we had a function like this, the function's not defined at a, but we can define the limit. However, when we compare 3, does that equal to that? We would say no, it doesn't equal to that. So stopping here, it's fine. With the function like that, even though the limit exists, doesn't matter that the limit exists. The function's not defined there. There's no way that these two things are going to be equal. Does that make sense? Even if one is true or one is false, we can't define, but the limit exists, doesn't matter. This is still not continuous at A because of number one. Is that what you were asking? Any other questions about this? It's good that we're hashing this stuff out. So function 2, is it continuous at 3 and 4? No, how come?
Well,
Yeah.
the domain
Right.
would not equal -3 or 4, because if you open it up on the bottom, you get x minus 3 and x minus 4.
Right, x minus 3, x minus 4. So it might not be totally obvious until we factor these things. I mean, we've always factored these kinds of functions anyways. But I would know if I didn't want to factor it, maybe I'm lazy and I didn't want to factor that. Can I plug 3 into this function? Just compute 3 squared minus 7 times 3 plus 12. It's going to give you 0. And you say, oh, well, I'm dividing by 0. There's no way I could do that. Plug in 4 to x squared minus 7x plus 12 also gives you 0. So again, no, the function's not continuous at 3 and 4 since f of 3 and f of 4 do not exist. So I'll put another example in here. Example 3. F of x equals to natural log of x. I'm sorry, just kind of arbitrary, but we did this. So is the natural log function continuous at a equals to 0? Can we plug 0 into a natural log and compute it? No. Remember, the domain of this function we already stated. Here's the domain of that function. It's the same reason, no, it's not continuous at 0, because f of 0 does not exist. It's not in the function's domain. What if I asked, is the natural log function ln x continuous at a equals to 2? What would we say?
Yes.
Yeah, 2 is in the function's domain, right? So I know we don't want to look at stuff visually, but visually here's the graph of the natural log function. Here's an x value of 2. Not only can we define that, ln of 2, but we can also approach 2 from both sides. And it's going to have that specific limit. That limit is the function value. know there's some justification to do here, but again, if you can think of continuity in the question of asking what the function's domain is as virtually one and the same thing, then you can determine whether it's continuous here, here, or here, just based off the function's domain. So I've kind of restated that here. We see a lot of theorems that are really technical to follow, but all they're saying is that things we've already know. These things we're presented to are talking about continuity at a specific point, but you'll notice that it still boils down to the domain of any one particular function that we're talking about. So the theorem 2.9 gives us continuity rules. So notice it says if f, the function f and the function g are continuous at a, then all of the following functions are continuous at a. So if I add two continuous functions at a specific location, subtract, multiply by a constant, divide them, or raise them to a power, it does not affect continuity. So what that's showing you, this theorem is, in short, it's saying that none of these operations among functions affects the continuity. These operations do not change continuity. And the only caveat is here. It's the same caveat we deal with every time we deal with a quotient of two functions. The quotient of two functions, it's continuous at a, provided that the denominator isn't 0. So it's really nothing new. So for this one, for part E, we could see those previous two examples. See the previous examples, 1 and 2. Do y'all remember, like, when we add two functions or multiply two functions together, like, how do we consider the domain? Does anybody remember that? Like, if I had f being the square root of x and g was like x plus 1, and then we compute f plus g of x. So there was a really technical way it said that the domain is the intersections of the domain of f and g. But if you know how to find domain, it doesn't really matter, right? Because then I look at this function, square root of x plus 1. What's the domain of this entire thing? All real numbers except what's affecting our input? Do we care about the x plus 1? We plug in any number there and add 1 to it? Yeah, the only thing that's giving us a problem is the square root. So if I plug in a negative number, I can't take the square root of it, even though I can add 1 to it. I can't take the square root of it. That negative numbers aren't in that function's domain because it consists of the square root. So really it doesn't, you know, if you forget how to look for the domain when you've given two functions and then you have to put them together like that, just put them together and say, well, what's the domain of that function? If that sounds weird or confusing, then maybe you need to look over to try to find a domain for various functions again. Because it is one and the same thing, continuity. Continuity of all of these functions depends on the function's domain. Theorem 210 deals with continuity of polynomial and rational functions. So a polynomial function is continuous for every value of x. Because we know polynomials functions, their domain is all real numbers. A rational function is continuous everywhere its denominator is not 0. So if we cross out continuous and just write defined, now we're back into a definition of what we would see in an algebra class. A polynomial is defined for all x values where the denominator is not 0. Continuity of composite functions. So remember, composite functions are where we put one function inside of another. It says that g is continuous, and notice here g, the f composed with g, that means f evaluated at g of x. So g is continuous at a. Let me write a. X. It's almost like x and a are interchangeable. You'll see a lot of things as we move forward with these with an x equal to an a. Just think about the a as a fixed x value, and x is any value. So once I say like x equals to 35, that's a fixed x value. That's what a is. So f composed with g of a. If the inner function g is continuous at a, and f is continuous at g of a, right? Because what we're plugging into f is g of a. F has to be continuous at its input. G has to be continuous at its input. If both of those are true, then the composite function is continuous. Let's see. Yeah, let me try to write this. So, for example, if f is the square root of x and g is, let's say g is x plus 2, the composite function is the square root of x plus 2. So really, when you look at a function in that way, you have to consider both or all operations that are involved in that function. So for instance, can I evaluate g at -4? Yeah, because g evaluated at -4 is just -2, right? So what we would say is, well, g, even though g, the function, is continuous everywhere, once I compose it with this other function, this square root, then I have to start worrying about what numbers does g output? What numbers does x plus 2 output? Because when x plus 2 is negative, I can't evaluate the square root of that. So g here is x plus 2. If g is continuous at any x value, which it is, f has to be continuous at g of a. So f has to be continuous at all outputs of x plus 2, because the outputs of x plus 2 are now the inputs of the square root. So again, I hope that's, it's just, we're talking about continuity here. It's no different than domain. Limits of composite functions. So we're talking about continuity of composite functions, and then this theorem goes into limits on composite functions. Notice the limit on the composite function here in both 1 and 2 is equal to, once we write this equal to, we're now passing the limit inside the outer function f just to the inner function g. Same thing, another composition, the limit is passed through into the inner function. And so, like, the example continuing with that is if you were asked to compute the limit as x approaches 2 on the square root of x plus 2, what we can do is pass the limit inside to the inner function and evaluate that first. And that, again, is building off of a limit law that we already saw. This one is just more generic because it deals with any composition. But it's just like any other function we've ever evaluated. If I pass through the limit, if I pass the limit through the radical, and that's causing me a negative number, then clearly I can't evaluate the square root of that negative number. So how about the limit as x approaches -3 on the square root of x plus 2. I mean, we wouldn't say it's the limit, I mean, we could, the limit as x approaches -3, x plus 2. At some point, we're going to get to a statement that doesn't make sense. So this is the square root of -1. Can't do that. Can't compute that limit. So, I mean, it's just very technical in how it's worded here. Once you see it in practice, I hope you're familiar with these functions. It should be totally obvious when you can and can't do something. Again, you can't compute the limit here because, remember, the square root of x plus 2, if you think about it in a different way, the square root of x plus 2 looks like this. And we're trying to evaluate a limit over here. So what it boils down to is -3 can't be passed through there because -3 isn't in that function's domain. So let's just state that here. All of these things above all functions above. I know they weren't specific functions, but operations. There were two specific functions, polynomials and rationals. Everything else just dealt with operations on functions. But we're talking about the continuity. So all these functions are continuous on their domains. And that's the lens we were kind of looking through all of the limits we evaluated up to this point. We're saying, well, I can't evaluate this limit. Does the function simplify? Can I use the conjugate? Can I use whatever to evaluate the limit? And then, once we got to a place where things divided away or canceled, we just plugged the x value directly into the function to evaluate the actual limit, right? That's what we've been doing the entire time, sort of this direct substitution. And the technical reason behind, why we're able to directly substitute is based on the notion of continuity. So we'll say also continuity gives us the y behind direct substitution. Like whatever limit we have. So if we encounter that limit in like 2.3, we would just say, well, x is getting really close to 2. Let me just plug that in. So the reason we're able to just plug it in like that is because the square root of x plus 2 is continuous at an x value of 2. In other words, 2 is in the domain of the function square root of x plus 2. Yeah. Square root of 4 is 2. So, it doesn't seem like this, it doesn't seem very gratifying, right? Because we've been doing this all along, but the reason we've been able to do this all along is because of continuity. So, ta-da. All right, I think we'll take a break because we're going to shift gears slightly and talk about continuity not at a single point, but along an interval. Yeah. So let's take a break and we'll come back and talk about that. All right. So I want to point out also, we're not yet in chapter 3, of course, but the notion of continuity does play an important role with derivatives and theorems that involve derivatives. So we'll try to point that out once we get there, but it's hard to show that right now. So how we're going to talk about continuity along an interval is if it's continuous at every point on the interval. So it's not that we have to check continuity at every point because that would be impossible. But we started with the point definition of continuity, and then we can extend that to all points within a certain window. These two graphs here, though, illustrate that we do have to be careful when we talk about continuity along an interval, because we can see here a specific label for the function on the left and a specific label for a function on the right. And how the interval of continuity is different for both of those functions. Again, that's going to depend on the function itself, but this function here on the left is right continuous at a because the function value exists at a, so whatever that is, f of a, and the limit exists at a, but only in the context of a one-sided limit. So as I approach a from the right, that limit is equal to the function value. So we're going to have to discuss right continuity, or this thing is continuous from the right, and continuity from the left. Again, left continuous at b because f of b exists, and we can only approach b from the left. The limit as we approach b from the left does equal the function value, and therefore we would say this is left continuous at b. So notice in either instance, whether we're talking about right continuous at a location or left continuous at a location, what that's doing is it's closing off or making a square bracket around that particular value. We've seen this kind of notation before when we deal with domains, like the square roots domain, for instance. But now again, we're thinking about this through the lens of continuity. Looking at the graphs, both right continuous at A and left continuous at B, looking at the graphs, it should be really obvious the interval of continuity, right? We include A, but we don't include B. Here, we don't include A, but we do include B to get these two intervals. But looking at a graph, it's totally obvious what those should be. But again, we're going to look at that through the lens of computing limits. So some of these examples you'll look at and you'll say, well, isn't it totally obvious where the function's continuous? Because most functions are continuous on their domain, but there are some exceptions where we have to be careful. And that implies that we do look at one-sided limits, not two-sided limits. So how we're going to define continuity at the endpoint is exactly how we defined continuity at a particular point, except we're now looking at one-sided limits. So in order for us to be continuous from the left, the limit as we approach A from the left has to equal the function value. And notice that's the exact same definition we had for continuity at A prior to this. It's just now in some instances it makes sense to only look at a one-sided limit. So that's the only modification that we've done here, is turn the two-sided limit in our previous definition of continuity into a one-sided definition. So really, if we're talking about continuity on an interval, the question is really what's happening at the endpoint. It's not, well, the function's defined for all of these values in between, but what's happening out on this end and what's happening out on this end. So in order to define continuity at an interval, we have to say that it's continuous at all points in the interval. If the interval I contains its endpoints, continuity on the interval means it's continuous from the right and from the left. So again, something we've already seen before, but we would say that, this function is continuous from A to B. Unlike the two examples in the graphs above, where we have to say that it's right continuous at A or left continuous at B. So in other words, think about starting with parentheses at the endpoints always, and then just using a one-sided limit to determine, does that parenthesis turn into a square bracket or not? And the parenthesis turns into a square bracket if these two things right here are true. Now, that's like an oversimplistic way to think about it, but that's essentially what we're doing. So this notation here is that's all we mean. If we have a function like this, then f of x is continuous on that interval because we're including the endpoints. So hopefully when you see the visual behind what we're talking about, that the definition of continuity at an endpoint and the definition of continuity along an interval aren't too daunting. Does anyone have any questions on that? So just to give us another example, what if we had a function that looked like this? And this is f of x. What would we say is the interval of continuity for that function? So, but there is an interval where it's continuous, right? It's continuous at all of these values here.
It just doesn't include A or B.
Right, we don't include the endpoints. F of x is continuous on the interval A to B. Just don't include the endpoints. Again, from a visual graphical perspective, it's nothing you haven't seen time and time again. Hopefully, it might have been a long time ago, but so visually these things, like with our previous example of that graph, visually they should be easy to determine where this thing's continuous. But what's tedious and what might not make a lot of sense is when we actually just look at a function and don't think about its graph and just compute these limits to come to these conclusions. So, for example, if we're given this piecewise function here and we were asked to determine the intervals of continuity, what's the easiest way to determine the interval of continuity? And we'll see if there's any flaws in that logic. The idea is that you really can't be sure, maybe you can. We'll just pretend. You really can't be sure if it's continuous where you think it's continuous. without computing limits. Because that's how we defined continuity in terms of a limit. But where might we guess that this function would be continuous on? What are the intervals of continuity for this function? On its domain, right? We would say, okay, well, the function has to be continuous on its domain. So the domain of the first piece are 0 and a value smaller than 0. And we know just from an algebraic perspective, what we're describing is the interval from negative infinity to 0, including 0. The second piece, we do a similar thing with that. Doesn't include 0, but everything larger than 0. Yeah? So now in the sense of our new terminology, the top piece's domain, what would we say about continuity at 0?
It's not continuous at 0.
So would y'all say that that top piece is not continuous at 0?
Be left continuous.
Yeah, we're including it. We're including it in that piece. It has to be continuous there. But it doesn't make sense to say on this top piece that we're right continuous at 0, because this domain doesn't allow us to approach 0 from the right. It does allow us to approach 0 from the left. So this is left continuous. At x equals to 0. This is not how I want you all to work these problems at all. It's just I'm trying to build off information that we already know about these functions to show you the appropriate work that's involved and how it does tell us the exact same thing. It's just, honestly, it's just more tedious. Nothing I can do about that. What would we say about the second interval? Is that right continuous at 0? No. So we can approach 0 only from the right, but this is not right continuous at x equals to 0. So a lot of these, a lot of the complexities, I guess, if there is, involved with especially piecewise functions can be solved just by drawing out their domain. When you're computing limits, as we saw, when we're talking about continuity, a lot of those questions can become really obvious once we see visually what's happening on each piece. So really what this boils down to with a piecewise function is, are the pieces actually connected or are they disjoint? Are there two separate pieces or do they come together at a common y value? So when we're asked to determine the intervals of continuity, the only x value that we have to pause and sort of do work involving would be what in this example? Would be x equals to 0, right? Because we have something weird happening here at 0. One piece includes it, the other piece doesn't. Every other x value is completely contained in either the top or the bottom. It's only at x equals to 0 where we might have that jump or that break. Okay. So really what we need to determine is f of x continuous at x equals to 0, because we see that the function is continuous everywhere else. Is that obvious? That the function is continuous everywhere else but 0? So I'll just write that out. We know that f of x is continuous everywhere else. So this is our question that we're answering. So basically this has boiled down to, it asks us to determine the intervals of continuity, but a lot of the interval was already obvious based on the domain of each piece. So really now this question has boiled down to, is the function continuous at a point? So now we're kind of translating this back to what we did first. So continuity, we have to use the checklist. We're going to check. Number 1, does f of 0 exist? Yeah, f of 0 is what? F of 0 is defined on the top piece. The top piece includes 0. That y value is 0 squared plus 1. So yes, f of 0 exists. Number 2, condition 2 of the checklist is what?
What's the limit of x approaching 0?
Right. Does the limit as x approaches the value in question on the function exist? No, how do we know?
You get two different values for different pieces.
Yeah. So it's obvious to y'all that the y values are different. There's a real simple way to check that, but that's not what we're after here. What we're after is justifying in the sense of a limit. So how do I compute the limit at 0 on this piecewise function? We already talked about it. Well, there's potentially a gap. So the two-sided limit as x approaches 0, it doesn't make any sense to compute on this function. So in order to answer item number 2 on the checklist, we now have to look at a one-sided limit. So this is 2a. We're going to have 2a and 2b. So 2a, does the limit as x approaches 0 from the right on that function exist? If I approach 0 from the right, which piece do I use? The bottom piece, yeah. Let me erase this from our previous discussion. I can only approach 0 from the right if I use the bottom piece. So that's 3x plus 5. I'm going to erase this, running out of space. So what's the limit as x approaches 0 on 3x plus 5? 5. So what is that telling us? So for the two-sided limit, we would have to know what the limit from the left is as well. So we don't know yet about the two-sided limit.
We just know that the right side approaches 5.
We just know that as we approach 0 from the right, the limit is equal to 5, and we know the function at 0 is equal to 1. So what does this limit right here tell us? Close. We're approaching 0 from the right, therefore the function is not...
Right continuous.
Yeah, right continuous. The function isn't right continuous at 0 because as I approach 0 from the right, I get 5, but the function value at 0 is actually 1. So remember, if this, let's pretend for a second that this wasn't here. The 0 from the right wasn't here. If I said the limit as x approaches 0 on this function is 5, but the function value at 0 is 1, from previous examples we would say that function's not continuous at 0, right? Because the limit has to equal the function value. The only modification we're making is now we're looking at a one-sided limit. So I can't say that the function's not continuous at 0. I can say now the function is not right continuous at 0. So this does not equal to f of 0, which means that f of x is not right continuous at x equals to 0. So now we know a portion of the interval where the function is continuous. If it's not right continuous at 0, then as I get closer and closer to 0 from the right, all that tells me is that I still have to have a parenthesis around 0. If it were continuous at 0 from the right or the left, then that's going to tell me when I can close off the parenthesis. So I know where it's not continuous, therefore I know where it is continuous. So if it's not right continuous at 0, then it is continuous sorry, that's left. Then it is continuous approaching 0 from the right. It is continuous on that interval. So as I approach 0 from the right-hand side, this limit is not the function value, therefore I can't include that into the interval of continuity. Questions on that? Does that jive with what we said up here? Yeah, it's not right continuous at x equals to 0 because this piece right here didn't include that value. So we're just using this as a guide. What we're doing here with the limit is the technical way to justify that. Okay, and a similar approach, 2b, we have to then compute the limit as x approaches 0 from the left. If we approach 0 from the left on this function, I have to use the top piece. And we see that limit comes out to be 1. The limit from the left is 1, which is the function value. So what does this mean?
It's left continuous at x equals 0.
The function is left continuous since the limit from the left equals the function value. So f of x is left continuous at x equals to 0. That is, as we approach 0 from the left, we can close off the parentheses. We now have a square bracket at 0 from the left. So that's those two things we got from looking at one-sided limits. Those two intervals we've listed are the intervals of continuity for that function. So that's our answer. That's our interval of continuity. So at least on the surface, it seems a lot easier to look at just the domain of each piece and determine the intervals of continuity that way. The next example will illustrate sort of the error in just doing that. Are there any questions on that first example, though?
So then the limit doesn't exist, right? Since the two-sided limits don't equal.
Right, yeah, and then it didn't ask, but then we could take that further. does the limit as x approaches 0 exist? Well, here's our work to justify that. This limit was 5, the other limit was 1. The limit as x approaches 0 then does not exist because the one-sided limits in 2a and b are different. I'll just write it out like this. 2a is not equal to 2b. So since those intervals don't join up, we're not including 0 from the left and from the right, we have two different components to that piecewise function. One graph is over here doing this, the other graph is over here doing this. They're not connected. If those two pieces were connected, we would see these intervals become connected. So this one here, example 2, it's the same idea. Is this function continuous at 1? Because the intervals of continuity, we know that all x values are larger than 1, those are all okay. All x values smaller than 1, those are all included in the interval as well. The only questionable location is at x equal to 1. So the first question on the checklist, can I define f of 1? Yeah, f of 1 is equal to 4. Okay, the second item on the checklist asks, can we compute the limit as x approaches 1 on this function? Now we're back in where we look at these in 2.3. In 2.3 we said, well, I've got to now look at a one-sided limit because I'm not sure about those two intervals. So here's 2a. Does the limit as x approach 1 from the right on this function? So as x approaches 1 from the right, which function piece do we use? The top one, approaching 1 from the right, those values are slightly larger than 1. So we're going to use the top piece. So as x approaches 1 from the right, that limit is 4. The function value at 1 is also 4. What does that mean? It's right continuous. This function is right continuous. So f of x, our conclusion here is f of x is right continuous at x equal to 1. And saying that it's right continuous at x equals 1, we then need to translate that into an interval of continuity. So if it's right continuous at 1, what is the interval of continuity? I can approach 1 from the right-hand side, and I can include that. So what would that interval look like?
So like the square bracket.
Square bracket,
1.
1. But where is that? Is that over here, or is it over here?
It's on the left and then.
Yeah, because we can approach 1 from the right. I can approach 1 from this direction and then stop at it. So I'm approaching 1 from this direction and stopping. We need to write out, since the limit as x approaches 1 from the right on f of x equals f of 1, f of x is right continuous at x equals to 1. All right, so that's virtually half of the problem. And then we look at 2b, the limit as x approaches 1 from the left. As we approach 1 from the left, I have to use the second piece, which is 4. The limit as x approaches 1 on the function 4 is 4. And again, we see that this limit is the same as f of 1.
Question.
Yeah.
Would it be like wrong to notice that right away and just put negative infinity to infinity for the interval because they're equaling the same thing?
Yeah. So the question was, would it be wrong to notice it initially and just put negative infinity to infinity? And the answer is yes, because you haven't used any limits to justify your work. You've only used like a visual, more or less, a
Like
visual.
you do 2a, 2b without even looking at the interval just yet, and you wait till afterwards.
So say that again?
So you do 2a and 2b, but you wouldn't write the stuff in red just yet? And then at the end you put negative infinity to infinity.
Oh, yeah, if you have this work, yeah, if we didn't write this conclusion here, and we just concluded everything at the end, there's nothing wrong with that. I just want to take this one step at a time. It's super important that we realize when we compute these limits, because like in this last problem, if we didn't stop there, we compute this limit and we compute this limit, like it doesn't illustrate what we're actually doing with these one-sided limits. So all I'm trying to do is illustrate what this specific computation gives us in terms of continuity and what this specific computation gives us in terms of continuity. If you can make both of these computations and then conclude at the very end, it's really the same thing. I'm just showing you step by step what unfolds as we do each one of these steps. So it's okay to conclude at the very end. Same situation, we've got the limit from the left equaling the function value. So f of x is left continuous at x equal to 1. Therefore, the interval of continuity, now I can approach 1 from the left and close off the bracket since it's left continuous. So now our interval of continuity is this. And I'm not saying that now our interval continuity has changed. We're just looking at the individual pieces of that function. So really what we should say now is, now I have a clear sense of what the interval of continuity is for the entire function, since I have the interval of continuity for each piece. But notice the limit from the left and from the right are both 4. So from there, we can go back. So from this fact and from this fact, we can go back up here and say the limit as x approaches 1 is also 4. So since the limit as x approaches 1 equals 4, and the function value at 1 equals 4, what do we know about the function?
It's continuous.
It's continuous where?
On its entirety.
Yeah, so this is a point-wise continuity. 1 and 2 has shown us that the limit is equal to the function value, therefore the function is continuous at x equal to 1. Meaning that the two pieces have come together. But we don't get that until we compute both of these limits and see, oh, they're exactly the same. Another way to look at that is these two intervals we've generated. Well, it's closed off one from the right and from the left. So that means it includes 1 from both directions, right? I can approach it from this direction and I can approach it from this direction. There's no need to compartmentalize and shut it off. So these two intervals, let's just write this out just so it's clear visually anyways. The first interval says I can approach 1 from this direction and include it like that. The second one says that I approach 1 in this direction and then I include 1 like that. Right? I mean, that's visually what we're showing with those two intervals. But that doesn't make a lot of sense to look at it that way. Because we know it's all together now. So this interval is really this interval. is continuous on all real numbers. So it's 4 for smaller than 1. So if we were to graph that, looking at graphs, then it becomes really obvious. If we were to graph this, here's our first piece, or our bottom piece, doesn't include 1. The second piece comes in and it includes an x value of 1, but more importantly, its y value is also 4. And then it's this quadratic here like this. If we looked at the graph of this first function here, this graph is actually in your textbook, so the graph of this first function, we have this piece that's quadratic here, like that, and then a line that goes off in that direction. So looking at the graphs, it's totally obvious. Hey, this thing's continuous from negative infinity to 0, including 0, and this piece is continuous not including 0 off to infinity. Same thing with graph 2. We can see that that's continuous on all real numbers, just by looking at it. But we want to avoid having to graph stuff to know about it. So what question, or are there any questions on this? Yeah.
So on just part A and B, if like on that last one, if it hadn't equaled 4, it would just be, you just put a parenthesis instead of a bracket
Right.
on the 1. Okay,
Yeah.
so that's all you're determining, whether it's a parenthesis or bracket.
Yeah, exactly.
Okay.
Yep. Yeah. As we stated earlier, that's all these limits, one-sided limits and continuity are addressing is if whether we have a parenthesis around the number or if it's a bracket around the number. That's it. And you might say, well, can I get that from looking at the function? Yeah, you totally get that information from looking at the function. But again, if we did that process here with this graph, we would say, well, this piece is everything larger than or equal to 1. And the second piece is everything smaller than 1. So notice that's a very similar situation we had in that first example, where we're questioning what's happening here in the first example at 0, the second one here at 1. The difference here is that the first function, the two pieces of the graph didn't meet. So if they don't meet, then this closed point doesn't fill in the open circle. When they do meet, then we have that situation like this right here. This thing comes in and fills off that closed, or that hole, and then we continue on. But really then all that equates to is, what are the y values on each piece as I approach 1? So I don't know if those are connected, right? But then I can look at, well, what's x squared plus 3x at 1? It's 4. And this function at 1 is also 4. So since they have the same y value, they have to meet at the same location, right? This thing is filling in this thing. It was different here because we didn't know if they were connected or not. The top piece at 0 gave us 1. The bottom piece at 0 gives us 5. They're not connected because they don't share the same y value. So yeah, there's a much more efficient way to check it, just through an algebraic approach. But we're talking about a limit approach, so make sure you're working with limits when you do this stuff, even though it doesn't seem necessary. It is necessary. Were there any other questions on those two examples? continuity of functions involving roots. If m is odd, an odd integer is a positive or a negative whole number, then a function raised to the n over n power, if we take any function and raise it to the n over n power here, what kind of root are we dealing with? It's a radical, yeah. What kind of root though? What determines the root on these fractional powers? The numerator or the denominator? Denominator, m is an odd number, so we're talking about odd roots here. Odd roots are continuous at all points for which the inside function is continuous. So what that means is when we deal with odd roots, taking the odd root of any function does not affect its continuity. So odd roots do not change continuity. The second statement deals with even roots. And so what do we have to be cautious with even roots?
Take the root of a negative number.
Right, that's what's on the inside of an even root has to be positive, right? That's exactly what this is saying. If m is even, then the even root of this function is continuous everywhere the function is positive. Even roots are continuous when, I don't know how to write this, so I'll just say when we're taking the even root of something that's positive. Again, that's something we already knew. Doesn't make sense to take an even root of a negative thing, negative number. But what you'll notice is lacking there in that statement is why not 0? Why isn't that continuous when we're taking the even root of 0? Because I can define the even root of 0 as 0. So just note this theorem does not tell us anything about continuity when that f of a is equal to 0. So it's a little bit strange, you know, here's another time where it's slightly different than the function's domain. Because any even root, we would say, well, the quantity I'm taking the even root of has to be positive or 0. That's totally fine to take an even root of those types of numbers. But when we're talking about continuity, we're talking about that it's strictly larger than 0. That theorem doesn't say anything about what happens when it's equal to 0. So really the intention, and we might just mention this, we're not going to look at it because it's not on your homework or it's not on the exam, but really the intention is to say, okay, it's continuous on this interval with parentheses. Then you've got to look at the endpoints and determine, is it continuous from the right and left so I can close off these parentheses or not. So for what values of the of x is the function's root 9 minus x squared continuous? Yeah. So here, again, just think about the domain. A couple of ways to think about this. domain is when 9 minus x squared is larger than or equal to 0. Or we could try to graph that. Do y'all remember how to solve these inequalities? What does the graph of x squared minus 9 look like? 9 minus x squared, sorry. What have we done to the quadratic? Yeah, moved it up 9, and it's negative, so now it's opening down. So we want to know, when is this larger than or equal to 0? Here, it's equal to 0. Here, it's larger than 0. So what are these x-intercepts here? Nine minus 9 is 0, so that's 3 squared, and 9 minus 9 is 0, also negative 3 squared. So what's the domain of this function?
Negative 3 to 3.
Yeah, negative 3 to 3. So that's the domain of the function. Consequently, it's the interval of continuity for that function. Yeah.
So why would you think about the part below 0 that goes to infinity?
Because we're taking the square root of that quantity.
Okay.
So when that quantity, 9 minus x squared, is negative, all of these x values here and here cause us to take the square root of a negative number.
Okay.
The other way to think about this is the function y is the square root of 9 minus x squared. Let me square both sides, and then add x squared to both sides. What do we know this to be? Circle with a center of 0, 0, radius of 3. So this is a circle, center 0, 0 with a radius of 3. Is it the whole circle? No, how come it's not the whole circle? What is y? Y is only the positive root. So y values are always positive, right? These y values are always positive. So what part of the circle is it?
Right.
The top half, where the y values are positive. So the square root of 9 minus x squared is this top half of the circle. So then we look at the top half of the circle, radius 3, and say, well, it goes from negative 3 to 3. It's the same conclusion we drew solving the inequality. But again, it's just boiled down to, what's the interval of continuity? Well, what's the domain of that function? It's the same thing. The only difference we saw was when we're dealing with these piecewise functions, because sometimes they're connected, sometimes they're not. The handout is just a reminder for the domain of and range. Specifically, we want to pay attention to the domain of the trig functions, and especially the inverse trig functions. Oops, where is that? It's down here. Well, I guess I need to add that.
Is it on detail?
I think so. I don't know. The handout that I just passed out, or,
The
yeah,
handout.
should be. So this is, I don't know why that didn't print off or show up in your notes, but the handout is just to remind you, especially what is the domain of the inverse trig functions, because this theorem comes in and says the continuity of all of these functions are the function's domain. So if we know the domain of all of these functions, then we know where they're continuous as well. So here, we'll see the handout,
So we should definitely know the domain and range of all these trig functions and the trig functions.
Yeah, I mean, I think at this point you should. I know most of you probably don't. But knowing the domain is a super efficient way now, especially with this theorem, to also determine intervals of continuity. What's the domain for the exponential functions? Exponential functions are continuous on their domain. Domain of logarithms, we've seen this a lot today. Domain of logarithms, continuous on its domain, 0 to infinity. Before we continue, the types of discontinuities. So we've seen all of them before. We're going to put an appropriate jargon attached to them now. So one, we have a jump discontinuity. So just as it says, it's when you have a jump like that. It's a jump discontinuity. Two, we have a removable discontinuity. Removable discontinuity is just a hole. I know you've used the word hole for like a long time for these types of things. Try to switch that into a removable discontinuity. There's nothing wrong with holes, I guess, but more technically it's a removable discontinuity. And if you think about how holes arise in graphs, they're the factors that cancel out. They're the factors that get removed from the function, right? So we're removing, it has a removable discontinuity. And the third one is an infinite discontinuity. Infinite discontinuities are like vertical asymptotes.
On a jump, is one hole always going to be like open and one closed? Not that it really matters. but
Yeah, not
it
always.
is.
I don't know why we wouldn't, but if we did this though, we wouldn't be talking about a function anymore, so you typically don't see that.
Okay. I was just-
But still would be considered a jump. Yeah. All right. Do y'all have any questions at this point? No? Okay. All right, so another example, let's look at Remember, the continuity is the notion behind direct substitution. So in your homework, you do have one or two limits that show up again in 2.6. So let's evaluate the limit as x approaches pi over 2. Where's the function is 5 times sine x minus 1 over cosine squared x. So can we evaluate directly? Oh yeah, that's well, what's the cosine of pi over 2? 0. So we can't evaluate this directly. So the denominator is equal to 0. Normally we would just go into computing limits and stuff, which is fine, but I do want to point out the reason we can't evaluate this directly is because this function, 5 sine x minus 1 over cosine squared, is not continuous at pi over 2. So what is an option for us to do here to compute this limit?
You have to split up the cosine squared.
Okay, yeah. So how can we rewrite cosine squared?
I think something to do with sine x minus 1.
Yeah, so that's really close.
Sin x squared.
Yeah. So remember the Pythagorean identity that says sine squared plus cosine squared is equal to 1. So we use that to solve for the cosine squared, and maybe it's not immediately obvious why that's helpful or why we should take that approach. As you saw through a trig class or through pre-calculus here, when working with identities, it's not always obvious at all what you should do to simplify some of those things, right? There's so many different ways to represent. You really have to just take it in the context of my problem. What do I have? I have the cosine squared causing an issue, but I have a sine x minus 1 on top. So if I can get rid of the cosine squared, the only chance I have to get rid of cosine squared is through this factor of sine x minus 1. So sine x minus 1, I think, oh, that's kind of similar to a Pythagorean identity. And if you don't know that, then you're just kind of stuck. So these things aren't easy. Don't expect to look at something like that and be able to tell immediately what you should do, because that's just not the case with trig functions and solving trig equations, right? Maybe after a while you get a feel for it, but you really have to look at the context of the problem. What do I need in here to eliminate this issue? So even this, maybe not totally obvious why we want this, but 1 minus sine squared is a difference of squares. It would be great if this were already, sine squared minus 1 on top, but it's not. So we need to factor the 1 minus sine squared on the bottom, because that's still cosine. We haven't eliminated the issue of dividing by 0 yet. So that issue is still present. But the advantage again of writing cosine squared as 1 minus sine squared is now that we have it in this form, we can see that it's just the difference of squares. And that's going to help get rid of an issue that we have when we divide by 0. Just be careful, because these two factors are not identical. So don't just cross them out. They divide, but when they divide, what is that quotient? Yeah, the quotient's -1. This is positive sign -1, +1 minus sign. They're exactly opposites of each other. So just factor out a -1 from one of those. You'll have -1 times that. Those two will divide away and you're left with -1. So we'll have to finish this next time. But those two terms are canceling to give us -1. And now we don't have an issue of dividing by 0 in the bottom anymore. Alright, so do y'all have any questions at this point? Tuesday, we'll finish this, probably 5 more minutes on this section, then we'll start 2-7, and then we'll talk about the exam. Let me know if y'all have any questions coming up.